Welcome to today's Explainer. Today, we're going to decode exactly how Cambridge IGCSE math takes raw, seemingly totally random numbers and transforms them into powerful tools for understanding the everyday world around us. Seriously, if you've ever thought of statistics as just, dry numbers sitting in a textbook, prepare to have your mind changed. We're going to look at how data literally shapes the reality we live in, from the roads we drive on every morning to the exact way we read.
Here is a quick look at our agenda for today. We're going to cover data types and averages, visualizing raw data, cumulative frequency curves, and finally, math models and reality. Let's jump right in. I want to start with a really provocative question straight from the text about CDC growth charts. Think about this. Would all cultures use the exact same height charts? Like, if you measure a 16-year-old girl in the US and compare her to the 75th percentile on a US chart, does that same percentile apply globally? Well, the short answer is no. Absolutely not. And what that tells us about context in data is actually pretty profound. You see, genetics, diet, and environment vary massively across the globe, meaning our statistical baselines have to adapt to those realities. Numbers literally never exist in a vacuum. They always reflect the environment they were born in. Moving right along to Section 1, Data Types and Averages, where we master the absolute fundamentals of observation.
This brilliantly illustrates the crucial difference between what we count, like discrete cars passing a school gate, and what we measure, like the continuous time it takes to travel there. Think about it. You can't exactly have 2.5 cars passing a gate, right? So that data is discrete. But the time it takes you to travel to school, that could be 15 minutes, or 15.2 minutes, or even 15.24 seconds. It flows continuously. Knowing this difference is super important because it dictates exactly how we're going to graph and analyze the data later on.
Now, what's genuinely fascinating about this next example is how we can calculate an exact number, in this case, the mass of a missing rugby substitute, just by knowing how the team's averages shifted. According to our source material, the mean mass of 15 players is 85 kilograms. But when a substitute joins the pitch, making it 16 players total, that mean drops to 83.5 kilograms. So how do we find out his exact weight? Well, by multiplying the averages by the number of players, we find the total weight before and after the sub joined. The difference between those two totals reveals the hidden substitute's exact weight, which is 61 kilograms. It's honestly like mathematical detective work.
Now that we know our data types, let's head right into Section 2, Visualizing Raw Data. This is all about organizing the chaos.
So the crucial point here is that instead of just staring blankly at 30 random, totally disorganized cinema attendance numbers, we group them into structured ranges. Rather than listing every single screening's attendance individually, like 21, 30, 66, 71, and so on, we tally how many screenings fell into the 10 to 19 bracket, the 20 to 29 bracket, and so forth. Doing this instantly organizes the chaos, allowing us to super easily estimate the mean attendance per screening. It takes a total jumble of data and turns it into a clear, easy-to-read trend.
That brings us to Section 3, Cumulative Frequency Curves. This is where we track accumulation and figure out real-world reliability.
Let's look at a highly practical, everyday example from the text. A businesswoman records her morning commute times, and she's asking us to use statistics to decide if taking the motorway or the country roads is the more reliable choice to get to work. Specifically, she needs to know which route gets her to the office in under 25 minutes consistently. I mean, we all face choices like this every single day, right? But math actually takes the guesswork completely out of it.
By constructing a cumulative frequency table from her 20 days of driving, we can actually plot curves for both routes to find their exact median times. The cumulative frequency basically just keeps a running total. So by the 25-minute mark, she has made it to work 15 times via the motorway, but only 9 times via the country roads. By plotting this running total on a graph, we create an S-shaped curve that visually reveals exactly where the middle or median travel time sits for both of those options.
And this is where it gets really useful. This shows that while one route might actually have a faster median time, calculating a smaller interquartile range proves which route is genuinely more consistent and reliable day to day. The interquartile range, or IQR, looks at the middle 50% of the data. If that spread is very tight, it means your commute time is highly predictable. But if the IQR is wide, well, it means you might get to work in 15 minutes one day and 45 minutes the next, which is a nightmare. In statistics, a smaller IQR always equals greater reliability. Similarly, cumulative frequency curves are actively used to grade massive large-scale exams. Imagine 800 students taking a test. Instead of just setting some arbitrary made-up pass mark, examiners map all 800 scores on a cumulative frequency curve. The text notes that identifying the upper quartile mark on this curve strictly dictates the minimum threshold for achieving a grade 9. It's entirely data-driven, so when you sit an exam, you aren't just competing against the test paper. You are literally plotted within the mathematical distribution of your peers.
Which brings us perfectly to our final section, math models in reality. Here is how we start predicting outcomes with actual formulas. We can actually use math to objectively test bold newspaper claims like this one. Big money footballers are not popular with fans. I mean, is that actually true, or is it just a catchy headline? Well, the text shows us that by plotting 20 professional footballers' salaries on one axis against their popularity rankings on the other, we create a scatter plot. And by using a graphic display calculator to find the equation of the line of best fit, we can instantly see if there is a real, undeniable mathematical correlation between earning big money and being disliked by the fans. Math basically acts as our ultimate truth detector.
Another absolutely fascinating mathematical model from the text is the Gunning Fog Index. This index determines exactly how difficult a piece of text is to comprehend. Have you ever wondered why a tabloid newspaper is so much easier to read than a dense academic journal? It's actually not just a feeling. It's a measurable mathematical equation based entirely on the structure of the writing itself.
To calculate it, you just follow a few surprisingly simple steps. First, you extract the total number of words, then the total number of sentences, and finally, the number of complex words, which are defined as words with 3 or more syllables. You plug those variables into the specific formula you see here, and boom, it spits out an objective, numerical reading age for any article. It's a brilliant example of taking something highly subjective, like the difficulty of a text, and turning it into a concrete, measurable statistical model.
So the next time you read an article, check a grading curve, or even just decide which route to drive to work, remember the math working silently behind the scenes. Whether it's predicting a reliable commute, measuring text difficulty, or setting the failure threshold on a huge exam, how might these hidden statistical models be impacting the decisions made in your own life today? Keep your eyes open, and you'll start to see these numbers literally everywhere. Thanks so much for joining me on this explainer, and keep questioning the data.